Hi, this is Mrs. Basin, and today we're going to talk about the ideal gas law. So ideal gases conform to the kinetic molecular theory, which we talked about earlier in this unit. So the two most important parts of this for ideal gases are that the volume of the gas is small compared to the space between them. So we kind of stated it as the volume of a gas is basically zero. And then the forces between the gas particles are not significant. So they're not attracting or repelling each other. So these two parts of the kinetic molecular theory tend to be most accurate at high temperatures and low pressures. So high temperatures because the particles are moving very fast with lots of energy, and low pressure because they're very spread apart from each other. So they're not compacted into a small space. These assumptions break down at high pressures and low temperatures. So high pressures because you have lots of particles packed into a smaller space, and low temperatures because the particles don't have as much energy and are not moving as fast. So we are going to only deal with ideal gases. So we're going to assume that all the gases that we talk about conform to that kinetic molecular theory. So because of that, we can use something called the ideal gas law. So the ideal gas law combines Boyle's law, Charles' law, and Avogadro's law and helps describe the behavior of ideal gases. So the formula that we use for ideal gases is PV equals nRT. So P is pressure, we've already talked about, V is volume, N is number of moles, T is temperature. So R is a constant called the ideal gas constant, and that value is always equal to 0.0821 liter atmospheres per mole Kelvin. So that will be a constant that you'll be able to use in all of these ideal gas law problems. Now, because of the specific units of the ideal gas constant, when you put values into the ideal gas law equation, they have to be in specific units. So it's not like with the combined gas law, where as long as the two values were the same, it didn't matter what the units were. For this one, it does matter which of those units are because they have to be the same as the ones in that ideal gas constant. So pressure has to be in atmospheres, volume has to be in liters, the amount of gas has to be in moles, and the temperature has to be in Kelvin. So when you're doing these problems, if you're given values that are not in those specific units, then you have to do conversions to get them there. Okay, so we're going to do two examples so you can see what these look like. So just like before, because all of these problems eventually are going to be all mixed together, we're going to make a list of our variables as we see them in the problem. So for this one, I want to calculate the volume. So I'm going to put V equals question mark to know that that's what I'm looking for. That's occupied by 0.845 moles. So N equals 0.845 of nitrogen gas at a pressure of 1.37 atm and a temperature of 315 Kelvin. And then like we said, that R value is always going to be 0.0821 liter atmosphere per mole K. So before we can use our PV equals nRT, we have to make sure that everything is in the right units. So N is in moles, pressure is in atms, temperature is in Kelvin, and when we solve for volume, it will be in liters. So again, they have to match up with those units of that R value. So then after that, just like before, I can substitute everything in. So 1.37 atm for pressure. Volume is what I'm solving for. 0.845 moles for N. 0.0821 liter atm per mole K. And then temperature is 315 Kelvin. So I'm going to solve for V. So I'm going to multiply all of these together and then take those divided by the 1.37 to get volume by itself. And if you look at the units, atmospheres will cancel, moles will cancel, Kelvin will cancel, and I'll be left with liters. So when I solve that, I'm still going to use my sig fig rule. So I have 3 sig figs here. I have 16.0 liters of nitrogen gas. Okay, so this next example will show us what happens when we don't start out with or not given all the correct units that we need. So for this one, I'm going to start it the same way. what is the number of moles of gas, so moles of gas is what I'm looking for, in a basketball that inflated to a total pressure of 24.2 psi with a volume of 3.2 liters at a temperature of 25 degrees Celsius. Again, my R value is going to be the same, 0.0821 liter ATM per mole K. Okay, so before I can solve this, I have some issues with my units. So this one is okay, because that one already has liters, but PSI has to be changed to ATMs. So we're going to use those pressure conversions that we talked about the other day. So for every 1 ATM, there's 14.7 PSI. So that gives me 1.65 ATMs of pressure. And then moles is what we'll end up having as our final unit. Temperature has to be in Kelvin. Right now it's in Celsius. So like we talked about before, we're going to add 273. So my temperature is 298 Kelvin. Okay, so now that I've done that, I can go back to PV equals nRT. Pressure 1.65 ATM. A volume of 3.2 liters. N is what I'm looking for, 0.0821 liter ATM per mole K. And then my final temperature, or my temperature for this particular situation, 298 K. So again, ATM cancels, liters cancels, Kelvin cancels, so I'm left with moles. That tells me what my final unit would be. So if I do the math on this one and solve for N, 2 sig figs is my lowest number of sig figs here because of my volume and my temperature. So I would have 0.22 moles of gas. So again, these are pretty straightforward. You just have to be careful with the units. That's where it can get a little bit tricky. So pay attention to the units as you do these. Write the variables down as you read through the problem and substitute them into your ideal gas equation and solve for the one that you are looking for.